So second example, we'll work things up in a slightly more complicated fashion. So we're going to do a thing where the random variable of interest is not the standard normal, but a more general normal. So in addition to the previous facts, let's just remind ourselves of those: a sketch, symmetry about 0, and total area being 1. Additionally, remember that if x has a general normal distribution with mean mu, variance sigma squared, then a transformation where you subtract the mean, divide by the standard deviation, has a standard normal. Okay, so second question. We're going to suppose that x has a normal distribution with mean 2 and variance 9. And now we're going to try and find little x, such that the probability of being less than that little x is equal to 0.4. So at this point, we might be a little unsure how to proceed, but what we can see is that what we're looking for is an inverse probability. In other words, we know the probability, and we're looking for the value of x. So we're looking at the inverse tables, the second batch of tables we referred to earlier. So first of all, we could look at our inverse tables, which is for a standard normal. We can find little z such that the probability of being less than that for a standard normal is equal to 0.4. Well, we can't do that directly because that won't be in our tables, but because there's symmetry and this total area is 1, we know that this little z must be less than 0. It's the area up to a value, little z, and the answer is less than a half, and so we must know then that z is going to be less than 0. If it's bigger than 0, the probability will be bigger than a half. So what we can find is the probability of a random variable being less than this number is equal to 0.6. That's in our tables. Equivalently, the tables might tell us the probability that z is bigger than that number is 0.4, and these add up to 1, so that has to be the case. So those are in our inverse tables. Putting that together and using the symmetry, we find the probability of z being less than minus 0.2533 is equal to 0.4. Remember, it's symmetric, so the probability of being bigger than a value in one tail is the same as the probability of being less than a value in the other tail. And of course, to get the two tails symmetric, you just change the sign. So what we found is the probability of a standard normal random variable being less than minus 0.2533 equals 0.4. Okay, so coming back to where we started from, we're looking for a general normal, and we found the result for a standard normal. And so all we're going to do now is, if you like, undo the transformation we've spoken of at the top, which converts for a general normal to a standard normal. We're going to undo that transformation in order to find this little x here. So we find x using the inverse of this relationship here. So z equals x minus mu over sigma. We just undo that, we multiply by sigma, and add mu. We find little x will be mu plus sigma times little z. The little z of interest, which is the one here, we found that. We can see mu and sigma in the question. So from the statement, we recognize that mu is 2, and the variance being 9 means the standard deviation is 3. And so if we substitute all this, we find that x as mu plus sigma z is 2 plus 3 times this value of z that we found here, minus 0.2533, and we get the answer 1.240. And again, at the end, it's worth making a little sense check. Okay, we're looking for a probability of less than a half. So the probability of being up to a certain point is going to be less than a half, means the value where we are should be less than the mean. The mean was 2, and we've got a value a bit less than 2. So it's looking about right in terms of a sense check for what we're looking for. So in this example, we've used the inverse tables, and we've also used the case of a general normal. And of course, you can make things steadily more complex. We'll do one more example showing a slightly more difficult problem. So we're going to deal now with the case where x has a normal distribution with a known mean of 1 and an unknown variance. And we're supposing we know the probability of being bigger than a certain value is 0.2. Okay, so it's a bit similar to the last one, not quite the same. We've got one unknown, that's to say sigma, and we've got an equation in this probability with a specified value. So we've got enough information to be able to find it. So, again, it turns out to be fairly simple. We remember our transformation. The probability x is bigger than 6 is 0.2. We can also say, by simply taking a transformation on both sides here, we take a transform, we subtract the mean and divide by the standard deviation, and we subtract the mean and divide by the standard deviation. And the trick when you're writing this down is where you have symbols, keep symbols, and where you have numbers, use numbers where you know them. So on the left side of this equation, where we had previously x, the symbol, we're subtracting a mean, dividing by a standard deviation. We keep those two as symbols. On the right side, we subtract the mean, which is 1, and we use the number 1. We divide by the standard deviation. We don't know that, so we have to leave that as a symbol. There's nothing else we can do. But now on the left-hand side, we can recognize this as a standard normal quantity. And for a standard normal quantity, we can use the tables to find the number such that the probability of being bigger than that number is equal to 0.2. Okay, so again, it depends on the tables you're using. But you might find this value 0.8416 directly as the probability of being larger than that is 0.2, or you might have to do 1 minus that probability in order to get 0.2. So this quantity then will be, of course, 0.8. So now we've got this 0.8416, which corresponds to 6 minus 1 over sigma. So now it's just arithmetic to finish it off. So we have 6 minus 1, which is 5, divided by sigma, is equal to 0.8416. And so sigma is 5 divided by 0.8416. So we get 5.941. And so that was our initial task, to find the value of sigma. The final example we'll look at involves a case where there are two unknowns, mu and sigma squared, but we've got two equations to help us find those. We're going to use tables, this little problem, to find mu and sigma, where we know the probability of x being less than a certain number is given, the probability of x being bigger than a certain number is also given, and we can use tables to solve for these two unknowns. So first of all, and I'm missing off a few of the details here, you need to sort of work through with me from your own tables. So first of all, the probability that a standard normal random variable is less than minus 1.5, we can find as 0.0668. So the value here, minus 1.5, wouldn't be in the tables, but plus 1.5 would be. And using the symmetry and the total area 1, we could find that using the inverse tables to get this quantity here. And I'm using slightly more approximate values here rather than going for lots of decimal places, so rounded just to one decimal place in this calculation. And secondly, an easier calculation from the tables, the probability the random variable is bigger than 2.1 is 0.018. So again, this one comes from the inverse tables. So these are the two bits you have to find from the tables, and now we're going to use the transformation which takes any normal random variable to the standard normal to go from these general situations here. So what we have is, if we make a transformation from z back to x, it'll be x minus mu over sigma from minus 1.5, and in this case x minus mu over sigma to be 2.1. So again, what we're saying is, the left-hand side we leave as symbols, z minus mu over sigma, which is x, z minus mu over sigma, which is this x, and the right-hand side we put in the numbers where we know them, and in fact in this case we don't know anything. So what we'll have on the right-hand side is just minus 1.5. And so we solve these. This is just two equations with two unknowns, then gives the final value. Mu is 152 and sigma about 13 1/3. And again, it's worth a little sense check. We've got a number here, 152, which is somewhere in between 132 and 180, which again is where you'd expect it to be, given these two small probabilities here, and a value sigma in some way reflecting the distance between these, again shows it to be a plausible value. So this example, a bit more complicated. We've done a number of different things. We've got the situation with two unknowns, the situation where we've used the tables backwards, the inverse tables, and the situation where we've had to use also the fact of symmetry and the total area being 1. So a number of different examples for the normal distribution. Just to conclude, it's a useful distribution for continuous data, and it has lots of other properties which we haven't looked at here, and particularly for error distributions. To remember the key properties of symmetry and total area being 1, also the transformation where you can take any normal random variable and transform it into a standard normal, and then familiarizing yourself with tables so you can work out various probabilities based on different bits of information. Thank you.